discuss group theory. Today I will discuss some exercise of group theory. And our first question show that the group A5 has 24 elements of order 5, 20 elements of order 3 and 15 elements of order 2. I will see the construction of A5 group clearly, because if you know the construction clearly, then you will understand any group, any subgroup in better way. So, today's topic is, at first I will see how look like the construction of A5 group. At first I will highly recommend you, if you don't see my previous video, at first see my previous video. At first see what is the permutation group. This topic in my group theory lecture. See the playlist. Let's come back our original question. A5 has 24 elements of order 5, 20 elements of order 3 and 15 elements of order 2. At first try to oneself, then see my video. The solution is very easy solution. We all of us know any permutation, we can decompose any permutation into product of disjoint cycle in S5. And we all of us know disjoint cycle are always commute. Consider in V5 the element which contain E, A, B, C, D. And here the elements of S5 must have one of the following from. We all of us know the form. One, the group itself A, B, C, D, E. And we can write this as A, B, B, C, C, D, D, E. Since number of transposition is even, so always this permutation is even permutation. That means each cycle is even cycle. That means when any cycle contain odd number of element, we all of us know, then we can write this cycle as even number of transposition. And any cycle which contain odd number of element, this cycle always even permutation, because type of cycle is A, B, C, D, E. This cycle contain odd number of elements, so obviously this cycle would be even. We can write this cycle as even number of element. That cycle in S5, the cycle contain 3 elements A, B, C. Since this cycle contain odd number of elements, so always we can write this as even number of transportation. So this cycle is even. Next, the cycle contain product of 2 cycle AB and CD. Here the number of transposition is 2. So obviously this type of cycle is even type of cycle, even cycle. And when other possibility, the only contain 2 cycle AB, and here the number of transposition is 1, so this type of cycle is odd, and other is identity, and identity always even cycle. So in those cycle in S5, only in A5 only contain this and this. And since we know when a permutation is written as disjoint cycle, as we know that a permutation is always written as disjoint cycle, then its order is LCM of this length of cycle. This is the order of any cycle. Since the permutation, this type of cycle is even, therefore A5 contain A, B, C, D, E, whose order is 5, A, B, C, whose order is 3, A, B, C, D, whose order is 2, order of this type of cycle is 2, identity, order of this type of cycle is 1. Means in A5, this type of cycle contain one cycle of order 5, one cycle of order 3, one cycle of order 2 and one cycle of order 1. Now I will see in A5 how many elements of order 5, order 3, order 2 and order 1. For this, all of us know the formula. All d order elements in Sn, how the formula is n factorial over 1 to the power alpha 1 to the power alpha 2 r to the power alpha r times alpha 1 factorial alpha 2 factorial r 2 alpha r factorial. Here alpha 1 alpha 2 alpha r is if the cycle of order 2 contain 2 cycle. Here alpha 1 alpha 2 alpha r is the number of transposition. Okay. This formula we can tell the elements of order 5 in A5 would be only 5 factorial and elements of order 5 in A5 A, B, C, D, E, this is equal to B, C, D, E, A, this is equal to C, D, E, A, B, this is equal to D, E, A, B, C and this is equal to E, A, B, C, D. This type of cycle are all equal cycle. So, the number of elements of order 5 are 5 factorial over 5. By this formula we can tell, and this is actually 24. So, the number of elements of order 5 in A5 is 24. Even permutation of order 2 are of the form A, B, C, D, E. And since the even permutation of order 2 are of the form A, B, C, D, E. So, in A5, A, B, C, D, which is always equal to this type of cycle A, B, D, C, B, A, D, C, B, A, C, D, C, D, A, B, which is equal to D, C, A, B. This can be equal to D, C, B, A and this can be equal to C, D, B, A. This type of cycle always would be equal, and here number of elements of order 2 is 5 factorial over 2 square times 1 2 factorial times 2 factorial and this would be 15. So, in A5 the of order 2 is 15. So, means actually A5 has 24 elements of order 5, 20 elements of order 3 and 15 elements of order 2. Okay. Our next example. This is also very interesting. The question is, suppose A is a subgroup of the permutation group Sn of odd order. That means A is a subgroup of Sn of odd order. Now I will prove this is actually is subgroup of alternative group An. This proof is very interesting and very easy. At first, just think on self how I will prove this part. Then see my video. Let's see the proof. This proof is very easy type proof. Suppose A is be a subgroup of the permutation group Sn of odd order. that means order of A is equal to odd, then we may prove it by contradiction. That means consider A is not be the subgroup of AN, but actually we have to prove A is a subgroup of AN. By contradiction I will prove it. Consider one cycle sigma belongs to A's such that sigma is an odd permutation and A is equal to the set containing the element alpha 1, alpha 2, alpha p union the set containing the element beta 1, beta 2, beta k. And consider this is even number and this is odd number. Multiply these subgroup A's by the odd permutation sigma. Then sigma is equal to sigma alpha 1, sigma alpha 2, sigma alpha p. Since I have multiplied this part by sigma, so these would be odd, and by multiplying this part would be even. Actually this is equal to A's, sigma is equal to sigma A's, and that imply by this expression, since sigma is equal to A's, that means that imply actually P equal to Q. Therefore order of A is actually, since P equal to Q, 2P equal to 2P which is equal to actually 2Q, since P equal to Q, and since this is 2P, that means this is actually even number, which is actually contradiction, because given the order of A is odd, therefore our assumption A is not subgroup of AN. This is wrong assumption, because since I have considered A is not be subgroup of AN, so I have considered one sigma belongs to A such that sigma is an odd permutation, because even permutation means this is belongs to AN. Since I have considered A does not belongs to the subgroup A, the permutation AN, but if we consider A does not belongs to AN, that imply order of A is equal to even. This is our wrong assumption, because given A is be odd number, so actually A is a subgroup of AN. This proof is very easy proof but very interesting. Any subgroup which is odd order, which is subgroup of Sn, this is actually subgroup of alternative group AN. Now I will see another type of exercise. Prove that for all n greater than equal to 3, all subgroup which is generated by 3 cycle is actually nothing but is AN in the permutation group Sn. Hence, all subgroup generated by 3 cycle is AN in the permutation group Sn. Let's see the proof. Since every 3 cycle is an even permutation, then every 3 cycle of Sn is actually the subgroup AN, because IJK, consider this 3 cycle, we can write this as IKIJ. Obviously this is the even number of transposition, so this is always belongs to AN in Sn. Now, if tau belongs to AN, that means that imply actually tau is an even permutation, and that imply actually tau is a product of even number of transposition. First, consider tau 1 tau 2 is not disjoint. Then from any product of 2 transposition, we can write 1 3 cycle. So When tau 1 tau 2 is not disjoint, then then we can write it as 3 cycle as above. But when tau 1 and tau 2 be disjoint, then consider these two transposition ijkm. Obviously this is disjoint. Here we can write this as ij ik, and the inverse of ik is ki km. Then this part would be ikj and this part would be kmi. Therefore, from any two transposition we can write this as product of 3 cycle. So our proof has done. Any subgroup generated by 3 cycle in Sn is actually An. I hope my all viewers have understood the geometry. Okay? Oh. Now I will see another exercise of Sn group. Show that if A's is a subgroup of Sn, then this subgroup is either every number of A's is an even permutation or exactly half of members are even, or exactly half of members are even. This is our proof. That means subgroup of Sn are either even permutation or exactly half of members are even. Here A is B any subgroup of Sn, and we defined A is bar which is equal to set of those sigma in A's such that sigma is even. Now we have to prove A is bar is a subgroup of A's, where this A's is a subgroup of Sn. This is subgroup because consider Fg belongs to A's bar. Fg belongs to A's bar means G are even, so their inverse also would be even, and the product of even permutation are still always even. We all of us know. So F composition G inverse are even permutation, and since F composition G inverse are always imply even, so obviously A's bar is a subgroup of the group A's, where A's is the subgroup of Sn. Here there exists two possibility. Either this A's bar equal to whole A's, or these A's bar contain A's. If A's bar equal to A's, then we are done. But if A's bar not equal to A's, then we need to prove A's bar equal to actually order of A's over 2. Actually we have to prove if A's bar not equal to A's, then exactly half number of even permutation. A's bar not equal to A's, then that imply there exists at least one odd permutation sigma belongs to A's. Consider one mapping F from A's bar to A's modulo A's bar, who is defined by f of A's equal to sigma A's, where for some A's belongs to A's bar equal to order of A's over 2, and we need to prove f is 1 1 and 1 2 mapping, and the mapping is defined as f of A's bar map to A's modulo A's bar, and defined by f of A's equal to sigma A's for any A's belongs to A's bar. For 1 1, A's1 A's2 belongs to A's, and this A's1 A's2 belongs to A's such that A's1 equal to A's2, and since A's1 equal to A's2, that imply sigma A's1 equal to sigma A's2, and since sigma A's1 and sigma A's2 are equal, that imply f of A's1 equal to f of A's2, and since A's1 equal to A's2 imply f of A's1 equal to f of A's2, That implies this mapping F is 1, 1. And for onto, there exists inverse for every H bar. So obviously this mapping is onto. So F is 1, 1 and onto. Since F is 1, 1 and onto, that means this mapping is bijective mapping. So order of H bar is equal to order of H bar modulo H bar. Hence order of H bar equal to order of H over 2. Therefore, if H is a subgroup of Sn, then either every number of H is an even permutation or exactly half of member are even. Today I will stop here. In my next video, I will discuss some exercise about normal subgroup and simple group. And I will highly recommend you, if you don't see my previous video of normal subgroup and simple group, at first see those video, then our next video would be so easy, because our next video only the exercise part. Okay, see you soon. Stay safe and stay positive always, and don't forget to subscribe my channel for more videos. Thank you so much.